Okay, so this is test VTP1, where I will be testing the spread of the VLANs between the switches, which are distributed via the VTP protocol. So first, let's view some VLAN information. And as you can see, currently there are 1, 2, 3, 4, 5, 6 proper VLANs. Each one represents a different section of the LAN, and we should also show the VTP information, so we can see that this VTP is on the Cambridge domain. In fact, all of the switches are, all of the ones in the LAN anyways, and we can see if this has spread to the other switches by issuing the show VLAN brief commands, and we can see that each one has successfully received all of the VLANs, and we can see that this is running in client mode, which is opposed to the switch which was running as a server. So this switch is distributing them to these client switches, and again these work all the way up to here. So they have all been distributed correctly. To VTP2, which is a quick test to demonstrate that the VTP has propagated the VLAN databases correctly, and that you can ping between them. So we can see from looking at these that in the VLAN database they each have, they all have the information about each VLAN, and the access switches propagate their respective VLAN out of their fast Ethernet ports. So we can see that a machine in VLAN 40 can ping a machine in VLAN 30. So if we do ping 10.1.30.4, it took a little while to find it, but it did find it in the end. And we can also do trace route on the same thing. We can see that all it had to do was go out of its own VLAN and into the other one. So into VLAN routing is definitely working, and VTP has propagated them correctly. But let's just try one more. So this is on the 20 VLAN, and we're going to ping the 10 VLAN. So 10.1.10.4. Again, it took a while to find it, but eventually it did. And we can do trace route again to see that all it had to do was go out of its VLAN and then into the other one. Okay, so this is test OSPF1, where I'll be testing and displaying that the switches all have formed correct neighbor adjacencies. So yeah, first thing is you can type show IP OSPF neighbor, and we can see that it's picked up all of the VLAN information from the other switches, it propagates them itself with the other layer 3 switch, as well as the Cambridge entry rulers, which are both on the fast Ethernet ports, which goes out to the WAN. Oh, and also the gigabit Ethernet port that goes out into the outside network to access to the internet. And I'll just make sure that that's also on the first layer 3 switch, which it is, and then on the Cambridge entry router again, you can see that it's got the two the two main layer 3 switches. It knows about the 10 network, which represents Cambridge 10.1, represents the Cambridge network, and then it also has the 192 networks, which each one will represent the link between the different branches. So the 192.0 section of that network represents Birmingham, and then the 1.4 network represents London, and the 1.8 network represents Cardiff. On the link between them, I should say. The actual addresses for each one. This is 10.1 for Cambridge, 10.2 for Birmingham, 10.3 for London, and 10.4 for Cardiff. And if we go on these and also check their adjacencies, we can see that they have the adjacencies of both Cambridge entry rulers. They both have, because this is on the 8 network, they both have a 192.168.1.9 address for the first RUA and 192.168.2.9 for the second RUA, and they are named so that the serial sub-interface name relates to the IP address name as well, so the frame relay can accurately handle the point-to-point connections between each serial link. But each one is just connected to both Cambridge RUAs. That's how they're set up, and that is proof that they are all connected. Test OSPF2, where I'll be testing the host connectivity between the Cambridge branch and the Birmingham branch. So for a quick recap, the Birmingham branch is on the address of 10.2, it's on the 10.2 network, and Cambridge is on the 10.1 network. So this PC is 10.2.1.2, this PC over here is 10.1.40.4, which is on the graphics VLAN. So if we go into here and ping 10.1, 10.2.1.2, oh no, ping. Well, the first time it obviously took a while to find it via ARP requests, but it does appear to actually be pinging. From now it seems to have it every time. I just had to double check, but well, it should be fine. That proves it. But just for the sake of it, let's test it the other way, or let's test it to another machine. Let's test it on a different VLAN. So 10.1.20.4. So let's go. Again, it takes a while for the ARP requests to pick it up, but once it has, they can ping each other successfully. So that was a test that shows that the OSPF is routing the information from inside the LAN outside to the WAN network. Right, so this is test OSPF3. We'll be testing the connectivity between the Cambridge branch and the London branch. So if the Cambridge computer we're using is got an IP address of 10.1.40.5, and the London's computer has got 10.3.1.2. So if we just open up that computer, this is PC3, and we set to ping 10.3.1.2, you'd see that it successfully can talk to this computer, and the reverse should also be true, so that's 10.1.40.5. Again, it can ping back as well. Okay, so this is test OSPF4. I'll be testing the connectivity between the Cambridge branch and the Cardiff branch. So the Cambridge branch, if we pick, say, this computer here that has an IP of 10.1.20.4, and we pick the Cardiff computer, which has 10.4.1.2, 10.1.4.2. Oh, I think I did that wrong. 10.4.1.2. Ping 10.4.1.2. Right, so we can see that you can successfully ping from Cambridge to Cardiff. Now let's try that the other way around. So we get the Cardiff computer, and if we ping 10.1.20.4, you can see that that is successful. So connections between Cambridge and Cardiff can connect successfully. So this is OSPF test 5, where I'll be displaying the connectivity between the Cardiff branch and the Birmingham branch, and this is to demonstrate that the routing, the OSPF and the frame relay routing work across the WAN. So if we first go to the Cardiff branch, which has an IP address of 10.4.1.2, and we try to ping 10.2.1.2, 10.2.1.2, we can see that that is successful in its connection across. So if we just try the same thing in reverse and ping Cardiff from Birmingham, so that's like pictures of 10.4.1.2. You can see that that again is successful. This is a test for OSPF 6, where I'll be displaying the OSPF inter-area routing by showing which neighbors each OSPF in the WAN has found, and how it can cross. But there are border rulers that have both Area 1 and Area 0 adjacencies. So for example, on the Cambridge ruler, if we type show IP OSPF database, right, we can see already that in its database it has, it's quite hard to see that, but it has Area 0 link states and link IDs, as well as Area 1. So that shows that it has that. And also, if we do show IP route, we can see it has the inter-area icon there, because these three networks, the 10.2, 10.3, 10.4, are each on separate areas, Area 2, 3, and 4 respectively, and this border ruler bridges the gap between Area 0 and the outside areas. Okay, so this is test STP1, where we'll be testing whether the spanning tree protocol will be able to switch the links around when one goes down. So to test this out, here on switch 0 for the accounting VLAN, which is VLAN 10, so this puts them on the 10.1.10 network. So if we go onto the main access switch here and we shut down the interface, so this is in face, this is 0.2. Yeah, this is okay. This is maybe starting at 0.2, and if we shut it down, it's gone red. And if we just fast forward time a little bit, we'll see that the other link has become green, thus confirming that STP has performed its function correctly. This is the test for STP2, where I'll be disabling the trunk port on the second VLAN, which is VLAN 20, and seeing if STP is able to respond appropriately. So the trunk port for this is F802, and you can see that's currently active. So if we go on here and we tell F802 to shut down, you can see that it's changed its state to down. Both links have gone off. If we just fast forward time a little bit, we can see that the other link has come on, showing that STP does indeed work. Test for STP3, where we'll be shutting down the link on the third VLAN, which is VLAN 30, and the trunk port, okay, that was this trunk port here, FA02 on this switch. So if we just tell that switch to shut down that interface, you can see that goes down, and both of the ports have gone off now. They're both, well, that one's in a kind of standby mode, but if we just fast forward time a little bit, we can see that the other port comes up, showing that the trunk port for this does indeed work. Okay, this is the test for STP4, where we'll be testing if the trunk link between the fourth VLAN, which is this graphics VLAN here, which is like it's everything on the 10.1.40 network. We'll test if that STP correctly reroutes it through this trunk port here instead. So the trunk port for this is FA2, and if we just tell it to shut that port down, you can see that it's changed it to down. The port has gone off. If we just fast forward time a little bit, we can see that the other trunk link has come on, so we can see that STP has worked properly. Okay, well, this is the test for WAN1, which is going to test if the Cambridge RUA, it's going to test the redundancy of the Cambridge RUAs. If one Cambridge RUA goes down, the other Cambridge RUA should function in its place, and any network traffic coming from the other branches from in the WAN should still be able to connect with the Cambridge network. So first thing we're going to do is we're going to shut down all the ports on the first Cambridge RUA. So shut down all the ports. Shut them all down, and then we'll see if pings from a PC onto Cambridge will work. So this is PC6 on the Cardiff network, so we'll test this. We'll see if that can ping 10.1.20.4. And it can. And if we watch the simulation of this, the simulation for PC6 to PC2, you can see they will not go down the Cambridge Route 1. It will only use the second one, and the packet on the way back will also go down the same route. So the WAN is still fully functional, even if one of the RUAs is completely non-functional. Alright, this is test pub1. We'll be testing to see if the computers on the LAN Cambridge network can communicate with machines outside of the network on the public internet space that is accessed via this border RUA and then through the ISP, which is in public address space. So this PC8 here is 192.168.4.2. This So if we go on this PC and we try to ping 192.168.4.2, we can see that you can indeed talk to people outside the network. Trace route on the same. You can see that it had to go out of the 10.1 network first and across the multi-layer switches before it was then transferred with the border router to PC8 in the end. Okay, so this is the test pub 2, which is going to test the connectivity between London and the outside public network. So if we go on the London computer and we try and ping the outside internet via this computer here, 192.168.4.2, so we go ping 192.168.4.2, you can see that it does indeed reach that computer. You can do trace route for the same IP. Then we can see that it has to do some additional steps. It has to leave its 10.3 network of London, and then it joins the 192.168.2.5 network to transfer itself from the border routers out into the multi-layer switches, and then from there it's then pushed back into the other border router that sends it to the ISP. Test Wi-Fi 2, which is going to test whether a Wi-Fi a piece of like Wi-Fi hardware can connect to outside the network. So this PC is 192.168.4.2, and this smartphone, which wouldn't usually have this application of being able to ping, but it can on Packet Tracer. So you can see that that pings just fine outside the network. You can do a trace route as well. We can see that it has to leave its VLAN to go out into the main network where the multi-layer switches are, and then it gets pushed on through the border router and then to the computer. This is test HSRP1, which is going to test what happens when the active layer 3 switch is brought down, because these switches propagate the IPs for the hosts and with the VLANs using DHCP, and they both create a virtual router, which is the gateway of what these VLANs are set to. But currently they will all be physically using this router because this is the active router. So if we shut down all of the links on this this switch, we should see all of these go down. And this multi-layer switch won't be doing anything more. And you'll see that from here right now, we've just seen that the OSPF adjacency have changed. But what we really want to see is that the VLAN groups, this has now become the active layer 3 switch for those VLANs. So now, even when we have a computer, currently will have an IP, but if we just change that to static and then change the DSP so it doesn't have an IP address, and then we can just see, oh, it immediately already got a new DHCP address. So even if one switch is completely down, DHCP will still function as it can use the secondary switch. Right, this is test HSRP2, where the layer 3 switch has been shut down, so there's only one layer 3 switch in use right now. So this is to show the redundancy, and we're going to check if routing across the LAN in Cambridge still works. So this is a PC on the VLAN 40, and we're going to test if you can get to VLAN 30. So 10.1.30.4. So to do an ARP request, but then it did find it. We can do a trace route on the same address. You can see that it went out of 40 and then straight into the 30 network. It didn't have to even really go down into the multi-layer switches. This is test HSRP3, and we're going to be testing if the Cambridge LAN can still talk to the London branch on the WAN even with one of the multi-layer switches down. So the London branch is 10.3.1.2. So if we ping 10.1.3.2, oh wait, 10.3.1.2. You can see that that does still connect just fine. You can see that it goes out of the 40 network and then it goes into the main network, and then it goes to the border router and then into the network of London, which is the 10.3 network. And we can see that the route that would take would be it's going to go, it goes through the multi-layer switch 2 before going to PC5.